Okay, so today we're going to continue talking about graph traversals, DFS and BFS. So we talked about this in the last session. We saw how to code them. We saw how to solve some problems with them. And in this session, we're going to code some of those problems, and we're going to solve even more problems. And if we have time, I might even give you another algorithm. So remember, we had depth first search. And the idea in depth first search was that you start from somewhere and you just keep going deeper and deeper into your graph. You just take edges out from where you are until you get to a dead end. And when you get to a dead end, which means that you have already seen all of the neighbors of the current node, you just go back as much as necessary so that you can find a different path, so that you can go somewhere new. Okay. And we also implemented DFS. We talked about the DFS tree for every connected component, or the DFS forest for the whole graph. And we talked about the properties of these DFS trees. So we said that if I have an undirected graph, every edge is either going to be in my DFS tree or it's going to be a back edge. It's going to connect some node to one of its ancestors. But in the case of directed graphs, we saw that this is not the case. So we can have tree edges, we can have back edges. These are edges that connect some node to its ancestor. We have forward edges. These are edges that connect some node to some of its descendants, one of its descendants, let's say. And then we can also have cross edges. And this is like edges between two vertices that are not really in an ancestor-descendant relationship. But we saw that we can have cross edges in the directed case only if we see the starting point of the edge after the end point of the edge when we're doing our DFS. Okay, so these were the properties there. We talked about BFS. The idea in BFS was I start from some point and I want to visit all of the nodes of my graph in the order of their distance to my starting point. So first I visit my starting point, then I visit all the points at distance 1, then all the points at distance 2, and so on. And we saw how to implement BFS using a queue, basically. And again, we talked about the properties of BFS trees or BFS forests. These are all kind of easy. Now, the problems that we were solving. So the first problem we solved was just reachability. Pretty easy. I have two vertices. I'm asking you, can I get from this vertex to that vertex? You can just do a DFS or a BFS, whichever you like. It will find it out for you. Connected components, same thing. For shortest path, we saw that BFS actually works. For cycle, we saw that we can do either DFS or BFS. And then the question is, do I have any edges in my graph that are not in the tree? Because any edge outside of the tree would give you a cycle. And the last thing that we talked about, and this is where I'm going to start this session, was topological sort. So the problem of topological sort is that you have a directed graph, and basically we think of edges as some prerequisite relations. So imagine that these vertices are courses, and these edges just mean that I have to take course 1 before I can take course 2. And so on. I have to take 3 before 2 as well. I have to take 2 before 4. So I want to have a permutation of my vertices. I want an order of taking my courses such that I respect all of these prerequisites. Another way of looking at it is such that every edge goes from left to right. Okay. So I just told you the sketch of the algorithm last time. We're going to actually implement it this time. So we saw two algorithms. One algorithm used DFS. The other one was just an ad hoc algorithm for this particular problem. So let's first talk about the DFS algorithm. So the idea in my DFS algorithm was that I'm just going to pick one vertex. For example, I pick vertex number 1, and I do a DFS from vertex 1. Now, what are the vertices that I will see in this DFS? These are all the vertices that are reachable from 1. So if I start from 1 and take a path, where can I reach? Okay, but that doesn't mean that I will see all of my vertices. Maybe I see only some of the vertices. But this gives me a DFS tree rooted at 1. Now I pick a vertex that was not in this original DFS tree, and I do a DFS from that vertex. So let's say that vertex 10, sorry, vertex 10 was not reachable from 1, so it wasn't in my original tree. I just do a DFS from 10. This gives me another tree, and I keep doing this. So as long as I have vertices that I have not seen, I just do DFS from a new vertex, and I get a new DFS tree every time. So I will have a bunch of DFS trees like this. And now I want to argue about the edges of my original graph. So we know that every edge that is in one of these trees was definitely present in the original graph. But what other edges could I have? Okay. So here's the thing. Can I have a back edge? Let's say, for example, I have an edge from this vertex back to this one. It is possible that I have a back edge, but if I have a back edge, that's a cycle, right? And if I have a cycle, I cannot have a topological sort, right? So you can imagine, I guess it has happened in UST that you have cyclic dependencies between your courses. So you cannot take any of the courses in those cases, okay? So hopefully, I imagine that my input graph doesn't have cycles at all. So to solve this, I'm just going to change my input, and I'm going to say it's a directed graph without directed cycles. Okay, because otherwise, if I do have a directed cycle, then the answer is just I can't do it. Of course, I could also say that my input is just any directed graph, but then when you find the package, you have to just say that it fails and there is no solution, okay? By the way, this is also now an algorithm for figuring out whether a directed graph has a cycle. You just do DFS and you just check if there are packages, because packages give you cycles, right? But by the way, a directed graph that doesn't have a cycle is called a DAG, directed acyclic graph. So let's say I have a DAG, and since it's a DAG, I'm pretty sure that I don't have packages. So I don't have to consider this case. I can just be sure that whatever edge I have in my original graph, it's not going to be a package. Now, can I have a forward edge? And remember, a forward edge was an edge that connects some node to one of its descendants. Yes, I can have that. So maybe I have, for example, this edge in my original graph. Or maybe I also have this one. I can have a bunch of forward edges. That's okay. Now, the next question is about cross edges. Can I have cross edges? Again, the answer is yes. For example, I can have a cross edge from here to here. But what do I know about my cross edges? I know that if I have a cross edge from U to V, I've definitely seen V in my DFS before I've seen U, right? Because otherwise, if in this DFS I had seen U first, I would immediately go to V from U. I wouldn't stay at U. And then this would become a tree edge. The fact that this is a cross edge means that in my DFS, I saw V before I saw U. Okay, so I can have these kinds of cross edges, but I have to always see V before U in my DFS. Now, can I have edges that go between trees? Again, yes, these are pretty much the same as cross edges, right? But I can only have edges from vertices that I have seen later to vertices that I have seen earlier. So I can have edges like this from here. I might have an edge to here, right? But I cannot have an edge in the opposite direction. I cannot have an edge from this center tree to the right tree, because again, remember, I did this DFS before I did this one. So if this edge was there, I would already put it in the DFS tree, and all of these will actually go into this DFS tree. Okay. So these are all the edges that I have. My edges are either forward edges, or they're cross edges, or like edges between two different trees. But in the latter two cases, I am sure that I have an edge from a vertex that I have seen later to a vertex that I have seen earlier. Okay. Now, here's the thing. I'm just going to print all of these trees from right to left. Okay. So first, I'm going to print all the vertices in this tree. Then I'm going to print all the vertices in this tree. Then I'm going to print all the vertices in this tree. And of course, if I had more than 3 trees, I would just do it. Now, what does this ensure? This ensures that all the edges that go between two different trees are fine, because their starting point is always printed before their end point, right? But now the next question I have to solve is, within each tree, what is the order in which I print the vertices? Okay, so I know the ordering between the trees. I know that I have to print the vertices in this tree first, and then the vertices in this one, and then the vertices in this one. But the question is, inside this tree, what order should I use? Now, if I have just one tree, again, I have the same situation as before. I can have these kinds of edges. I can have basically forward edges, and I can also have cross edges. So let me actually just do one tree here. Let's say I start my DFS here, and I keep going. This is my DFS tree, and at some point I go back and I go in a different way. And at some point again, I go back, I explore somewhere else, I go back, I go somewhere else. Let's say this is my DFS tree. And generally, I created it in the left to right order. So this is the order that my DFS visited these vertices, right? Now, I said that I can have forward edges. Okay. So what does this mean? If I can have forward edges, it means that I definitely want to print this node up here before this node down here. Right? So that's one thing that I have to make sure I always keep in mind when I'm doing the printing. And also, this is true for the tree edges as well, right? So every parent should be printed before its children. I know that for sure. But then that doesn't give me like a complete ordering on all of the vertices. There are many different ways to print these vertices so that all parents come before their children. And that's also enough to satisfy the rules for these forward edges. The problem I have is with the back edges. Sorry, with the cross edges. We said that we can have cross edges, something like this. But we can have cross edges only if this vertex, let's call it U, is seen after this vertex. Let's call it V. Okay? So as I'm seeing my vertices, I can give them an order. What is the order in which my DFS visits all of these vertices? So my DFS is going to visit this vertex first. Oh, that's a terrible color. This vertex first. Then let's say it visited this one, then it visited this one, then it visited this. Then it backtracked, came here, visits 5, 6, goes up, comes here, visits 7, goes here, visits 8, goes here, visits 9. Okay. Now, here's the thing. If you look at this DFS visiting order, every parent is visited before its child. So I will never have any problem with the parent-child edges, with the tree edges. I will also never have a problem with the forward edges, right? Because these forward edges, it's just like an ancestor. So all the ancestors are definitely printed before their descendants. And I wouldn't even have a problem here, would I? Oh, Yes, I would. Right, so the problem is that if I just print all of the vertices in the order that my DFS visits them, it means that I print 4 before I print 8. Right? And then I have an edge from 8 to 4. This is going to be a right to left edge. So that wouldn't work. What should I do? How should I change my order here? What? Reverse order of the DFS? No, but in that case, then I would print 9 before 8. So
but because it's 2 nodes, you search for the child which has the largest order.
yes. So generally, let's look at this. If I have this node, what do I know? I know that I want to print all of its descendants after the current node. So I will definitely first print this node and then try to print all of the descendants. But which descendant do I want to print first? The descendant on the right side, right? So it's not exactly the DFS order, but you can get it based on your DFS tree. So you create your DFS tree, and for every node, you have basically now an array or a vector of children, and these are in the order that your DFS visited them. But then you have to go over this tree again, and you have to say, I first see this node, then I see all of its children recursively. So first I'm going to see 1, and then I'm going to call whatever visits procedure I have recursively on 2. Now, when I want to write all the vertices in 2 and its subtree, I first write 2, then I go to the rightmost or the last child of 2 that was seen in the DFS, and I recursively print that. Then I come here, then I go to 5, I recursively print that. Then I come back, I recursively print 3, and so on. So if I do this, this ensures that I have an ordering that respects all of my edges. So let's say I have a bunch of other edges too. Let's say I have an edge from whatever, 9 to 3, let's say, and maybe I have an edge from 7 to 6, and maybe I also have an edge from 2 to 4. All of these edges. Okay, so here's what I'm going to do. I'm going to first try to print 1. And when I print 1, I print 1 itself first, and then I print its children. So now I want to recursively print 2. So I print 2 itself, and then I print its children. So I recursively call print on 8, which first prints 8, then prints 9. Now I come back to 2, I call it on 5. First prints 5, then prints the rightmost child, 7. Comes back to 5, prints 6. I go back to 2, I print 3, I print 4. Now, if you look at my edges, all of my edges are going from left to right. Okay. So 3 edges are easy to check. 1 to 5 is definitely left to right. 2 to 4 is left to right. If you have to check these ones, right? 8 to 4, 8 comes before 4. 9 to 3, again, 9 comes before 3. 7 to 6, 7 comes before 6. So what is my runtime? Basically, I'm doing a bunch of DFSs here, but again, I'm seeing every vertex at most once. And so that means that I'm seeing every edge at most once in all of my DFSs combined, right? So this part is going to take O(n plus m) time. So this part is O(n plus m). And then I have to go and process every DFS tree, but on every DFS tree, I basically have a print function that recursively prints everything. So I'm going over, again, every vertex and every edge of the tree exactly once. So this one is actually going to just take O(n) time overall, because my trees have at most n-1 edges overall. So my total runtime is still the runtime of the DFS, which is O(n plus m). Okay. Great. So that's a topological sort algorithm based on DFS, and I just gave you the basic ideas in the last session. Now we filled in all the details, but I told you that there is also kind of an easier algorithm for topological sorting. And this is my second algorithm. And let me just take, okay, I need to have a DAG, so whatever, let's just try to create one. Let's say this is my DAG, and I know it's a DAG because all of my edges are already going from left to right. Right, and I'm going to just number the vertices. So let's say 1, 2, 3, 4, 5, and 6. So someone has given me this graph in the input. Again, just the number of vertices, number of edges, and list of edges. Now I want to print a topological sort. Or again, just think of this as courses and dependencies between courses. So what is the first course that you can take? You can take a course if it has no prerequisites, right? It's exactly the same thing here. If I have a vertex that has an mean degree of 0, if I have a vertex that doesn't have any edge coming into it, I can always put it at the beginning of my topological sort. And if I have several of these vertices, I can put whichever I want at the beginning. So in this case, I have 4. I can put 4 at the beginning of my list. Now, because 4 is the first item of my list, any edge that goes out of 4 is going to go from left to right. So I don't have any problem with the edges going out of 4. I can just remove 4 and all of the edges that went out of it from the graph. Okay. Oops. I don't have the ability to just, okay. So I remove all of these. Now, again, I say, is there a vertex that doesn't have any incoming edge? And I have 2 of them here. I have 5 or 3. It's my choice. I can take whichever I want. In this case, I would take 5, let's say. I put 5 next. And then again, I say all the edges from 5 are going to go from left to right anyway. So I can remove 5, and the edges that go out of 5, I can remove all of these. Right? And I just continue this. Every time, just find a vertex that doesn't have any incoming edges, that doesn't have any prerequisites. In this case, I would find 3, I would remove 3. And then I find that 6 doesn't have any prerequisites, I remove it. I find that 2 doesn't have any prerequisites, I remove it. And then 1. And if I had thought of this and took a copy of that graph, you would see that this is a valid topological sort. But I erased my whole graph, so you can now see it on the video. Okay, but what is the runtime of this algorithm? How much time am I spending here? Look, so every time I'm finding one vertex and I'm removing this vertex and all the edges that are going out of it. So at the very least, I'm spending n plus m because that's the number of vertices and edges that I'm removing. But am I really doing anything else? No, because I can just keep track for every vertex of its in degree, how many edges are coming in. And as soon as it becomes 0, I can remove. So my total runtime is just O n plus m. Okay. Let's implement this. Okay, so as usual, let's say that I just read the number of vertices and the number of edges first. And let's say my number of vertices in this case is at most something like this. And let's say that for every vertex, I'm going to keep track of all the edges that go out of this vertex. So I'm going to keep the list of successors of this vertex. And I'm going to include vector. So basically here, successors of I is the vector of all vertices J such that there is an edge from I to J. Okay. Now I have to read M edges. So for M times, I just read two vertices U and V. And I just say in the successors of U, add V. Okay. But other than this, I said that in my algorithm, I want to keep track of how many edges are coming into every vertex. So I want to keep track of the in degree of every vertex. Let's do that too. So I'm going to do this. And IND of I is the in degree of vertex I. So the number of edges that start somewhere else and come into I. And of course, when I'm doing this, I have an edge from U to V, so I have to increase IND of V. Okay. Now, one very simple thing that I can do is that every time I can have a for loop that goes over all of my vertices and see who has an in degree of 0. But that takes a lot of time. I don't want to do that. I just want to keep track of all the vertices that have an in degree of 0. Okay. So I'm just going to have a vector. And I call this vector Z. This is the vector of all vertices that have an in degree of 0. Okay. And initially, I fill it out. So I say for every I from 1 to n, if the in degree of I is 0, just put I into Z. Okay. Now, when I'm writing my vertices out, I can only print vertices that have an in degree of 0. So I can only print while Z is not empty. So as long as Z is not empty, I say take some element of Z. So I'm going to take some vertex, for example, let's call it U. And let's say I take the last element of Z. Okay. And I say I want to remove this vertex U. So first of all, let's remove it from Z. Then let's print it, because I always forget to print. And now that I have printed U in my list, I want to remove the vertex U, and I want to remove all the edges that go out of U. Okay. So the edges that went out of U, I know where they went. They went to the successors of U. So I can say for every V that is a successor of U, the in degree of V is now going to decrease by 1. Because the edge from U to V doesn't exist anymore. So the in degree of V decreases. But now just here, I can do a check. I can say, okay, if this was the last edge that was going into V, and if the in degree of V has now become 0, put V into the set Z. So if the in degree of V is 0, Z dot pushback V. And that's it. It gives me a topological sort. Now, very importantly, I'm not going to continuously search for vertices that have in degree 0. I did it only once at the beginning, and this one takes ON. But after this point, whenever a vertex gets degree 0, I immediately identify it without having to search for them. And again, the same argument as before goes through here. Every vertex is going to be added to Z exactly once. So I'm processing every vertex exactly once as this U here. So the number of vertices that are added to Z and removed from Z is exactly n. And then for every vertex that is taken out from Z, I'm looking at all of its successors. So I'm looking at every edge exactly once. And the work that I'm doing here, it's just a constant amount of work. So my total runtime is ON plus n. Let's see, topological.cpp. I really needed to take a copy of that. Okay, here's the thing. Here's what I can do. I can just do Control Z until it comes back. Okay. And now I can give this graph. So it has 6 vertices And how many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. I have 4, 3, 4, 6, 4, 5. I have 5, 6. I have 3 to 6, 3 to 2, 3 to 1. I have 6, 2, and I have 2, 1. Okay, and this is the topological sort that it printed. So now I don't have to do that again. I can just write it 4, 5, 3, 6, 2, 1. And it's exactly the topological sort that I had. Okay, and my control Z's removed O(n) plus M, so I just put that back here. Okay, this is much simpler than the algorithm based on DFS, of course. But now let's do the algorithm based on DFS, because why not? So I'm going to just take a copy of the DFS that I had, and I'm going to call it topological based on DFS. And okay. By the way, this is the DFS that I had in the previous session, except that I put it on Canvas and I just added some things that print like where the DFS is going and what vertex it's visiting and so on. It's just DFS, right? But this was DFS on a graph that was actually undirected, but now I have a directed graph. So you see, I just had the list of neighbors of a vertex, but now I want to say that they're not really the neighbors, they're the successors, okay? And the only thing that I have to change is that when I'm reading an edge from U to V, instead of adding both in the list of neighbors of the other one, I just say in the list of successors of U, add V. And then my DFS and everything else is basically the same. So when I'm doing DFS from a vertex S, I say that I have now seen S, and for every successor of S, for every T where there is an edge from S to T, I just say if I haven't seen T, let's go to T, let's do a DFS from T, but let's also set the parent of T to be S. Okay, so this works for both directed or undirected graphs. I have a bunch of prints there. I don't want to remove them, but okay. So here's what I'm doing. I said that I'm going to start a DFS from vertex 1, but it's not going to see all of my vertices. So I'm going to find the first unseen vertex and do a DFS from that vertex as well, okay? So my DFS is now a little bit different. I'm going to do something like this. I'm going to say for every vertex from 1 to n, if I have not seen this vertex in my past DFSs, just do a DFS from I. Okay. And by the way, this sees every vertex exactly once. Okay. Now, my DFS also kept track of the DFS tree and so on, so I know my DFS trees now. Let's actually do an example. Let me just do this. I say I have a vertex 1, 2, let's say 3 here, 4 here. Let's say I have something like this. I have 5, 6, 7, 8, and let's say I have an edge from 8 back to 3. And maybe I can have some forward edges. Let's say I have an edge from 1 to 4 in my original graph. Maybe I can have some back edge, let's say from 8 to 5. Maybe I can also have a cross edge from 7 to 6. Okay. So this is my graph. And basically, I'm going to do DFS on this graph, and you're going to see what happens with the DFS. Topological DFS. How many vertices do I have? I have 8 vertices. How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I have an edge 1, 2, 1, 3, 1, 4, 3, 4, 5, 6, 5, 7, 7, 8, 7, 6, and 8, 5, 8, 3. Okay, so this is how the DFS works. It starts from vertex 1 and it says the parent of vertex 1 is 0, which just means that vertex 1 is a root. And then it goes to vertex 2, the parent is 1. Okay, it goes back. It says exiting vertex 2. It goes to vertex 3, the parent is 1. It goes to vertex 4, the parent is 3. It exits 4. It exits 3. It exits 1. So when it exits 1, my first DFS is over. But remember, I had this DFS in a for loop. So it goes and searches for the first vertex that it has not seen, and it starts a DFS from there. Now, the first vertex it has not seen is 5. So as you see, it started a new DFS, and it says that the parent of 5 is 0. Okay, so 5 is also a root. And then it's going to vertex 6, the parent is 5, it exits 6, it goes to 7, the parent is 5, it goes to 8, the parent is 7, it exits 8, it exits 7, it exits 5, it has seen everything. Okay, so it creates exactly this tree as the DFS tree. Now, what do I want to do? I want to first of all find all these roots. But based on the output here, it's pretty easy to find roots, right? A node is a root if its parent is 0. I could also keep track of the roots when I was writing my code here. Let me actually remove this one. So here's the thing. Whenever I'm starting DFS from a vertex I, that I is a root, right? But I don't need to remember them because I can always check the parent. And if the parent is 0, it's a root. So I said that I start from the root with the largest number, and I print that tree first. So I want to print this tree first, and then I print this one. Okay. So this is what I'm going to do. I say for every I now from n back to 1, if the parent of I is 0, so if I is a root, I just say print I. And print is going to be a recursive function that prints I, but it also prints everything that is a descendant of I. Okay. Now, a tiny problem here is that I kept track of parents. I didn't keep track of children, right? So let's do that as well. Let's say that for every vertex, I have its children. Okay, so children I is the list of children of I. And of course, in the order that they're visited, right? So when I set the parent of T to be S, I also say in the children of S add T. Okay. Now I have my children as well. I don't have to change anything else. That was the only place where I use parent in my DFS. Now I just need to write my print function. So I'm just going to have a print, and it takes some vertex S. It has to print S and all of its descendants in the tree. But we said that the order we use is that we first print S, and then we recursively print the last child of S, and then the second last child, and so on. So I just say print S, and then for the children of S, this is going to start from children of S dot size -1. So you could also use an iterator here, but I'm just basically saying I want to print the children of S in the reverse order. So children of Si. Okay. So that's it. And let me maybe also add a cout here, saying that the topological sort is this thing. Copy this. Okay, so this is the topological sort that it gave us. It says, well, it's printing from right to left for the trees. So it first prints 5, then it prints 7, then it prints 8, Then it goes here and prints 6. Then it goes to the next tree. It prints 1, 3, 4, 2. And you can check that this is indeed a topological sort. Okay. Great. Yeah, so a cycle is not allowed because if you have a cycle, nothing would work, right? So actually, let's add a cycle here. Where is the cycle? 5, 7. Oh, sorry. Yeah. I didn't see that. Yeah, so the result is invalid if you have a cycle. Yeah. I didn't mean to add that. Very sorry. I meant to add it in the opposite direction from 5 to 8. Yeah, now it works. Because of course, if you have a cycle, you don't have a solution. And you can also check for that. The way you can check for it is that if you have a back edge, that means you have a cycle and you don't have a solution. But this particular algorithm, because I was not checking, it just prints garbage if you have a cycle. Okay, so we did topological sort. Let's now solve some other problems. So I want to talk about bipartiteness. So a graph is bipartite if you can divide it into 2 parts and every edge goes from the left part to the right part. Another equivalent way of talking about this is to say it's 2 colorable. Okay, so if I can color the vertices of my graph with 2 colors, let's say red and blue, such that every edge has both colors at its endpoints. No edge can have the same color on both endpoints. That's called the 2 colorable graph. So my input is just going to be an undirected graph G. And as output, you have to tell me whether it is 2 colorable or bipartite. Is G 2 colorable? Okay. So I hope that you remember from basic graph theory that a graph is bipartite or 2 colorable if and only if it does not have an odd cycle. So if I have a cycle with an odd number of vertices or an odd number of edges, then of course it's impossible to color even that cycle with 2 colors. But generally speaking, if I don't have that kind of cycle, then it's 2 colors. But I can use DFS or BFS not only to decide whether the graph is 2 colorable, but also to give a 2 coloring if it is possible, right? Remember that both my DFS and my BFS basically just give me a tree, right? On each one of the connected components. Of course, here I can also assume that the graph G is connected, because if it's not connected, I can color each of the connected components separately. Okay, so let's say I have a tree, and this can be a DFS tree or it can be a BFS tree. I don't really care, right? And okay, let's say just one tree because I'm talking about one connected component. And I have 2 colors. So I have to color the root of this tree with one of the 2 colors, right? Either red or blue. And it doesn't matter. I can choose whichever color I want because I can just swap all the colors. So let's say that I make my root red. If I do that, then I'm forced to make all the children of the root blue because they're connected to the root. And then I'm forced to make everything in the next level of the tree red. And everything in the next level has to be blue, and so on, right? So if I only look at the edges of this tree, I don't really have a choice. The only choice that I had was what color do I assign to the root, but that was also not really a choice because I can just change all the colors of all the vertices. Okay, invert all the colors. So I don't have a choice. I have one way of coloring the tree. Now, both DFS and BFS give me a tree. So I have only one way of coloring it. And after I do that coloring, I just check, is it a valid coloring of the whole graph or not? Just check every edge. Because if I only look at the tree, I have no other way. This is the only thing I can do. right? So again, O(n plus m). And you can do either DFS or BFS. I honestly don't care. You just need a tree. Okay. Another problem that is interesting is finding strongly connected components. So when we have undirected graphs, we often talk of connected components. And generally speaking, two vertices are in the same connected component if there is a path between them, right? Now, strongly connected components is a component that is defined for directed graphs, and the idea is that U and V are in the same strongly connected component if there is a path from U to V and another path from V to U. Okay? So again, my input here is going to be now a directed graph. GVE. And my output is just going to be its strongly connected components. Or actually, I'm just going to write SCC. SCCs of G. Now, I can ask you for the components themselves, or maybe I just ask you for the number of strongly connected components. Okay. Let's go here. I had this nice example. Yes. And okay. So what are the strongly connected components here? Let's first try to figure it out by hand. So 1 and 2 are definitely in the same component, right? So because there is an edge from 1 to 2 and one from 2 to 1. So this is definitely one strongly connected component. So let's say this is one of them. Now, if you look here, I have a cycle between these 4 vertices. So all of these 4 vertices are reachable from each other, but none of them can reach 1. So these 4 vertices are also the same strongly connected component. But do I have more? Can I, for example, include 7? Can I reach 6 from 7? No. Can I reach 6 from 8? No. So this is another strongly connected component. Right. Now, again, I have a cycle here. I really like cycles. This is definitely a strongly connected component. And now, finally, this is a strongly connected component, just this one vertex. And this one vertex is a strongly connected component. Now you can check. You can check that if I look at any 2 vertices, U and V, if there is a path from U to V and also from V to U, then I've put them in the same component. Okay. And generally the same way that connected components give you a partitioning of an undirected graph, in a directed graph, your strongly connected components also give you a partition. So how would you suggest we go finding the strongly connected components of this graph? Oh, today is again one of those 50-minute sessions. Okay. So I just want to do it for 1 hour and a half. I don't know why. But okay, what's interesting about these strongly connected components? If you look at them, you see that there is a very direct correlation between them and cycles, right? So for example, if I have a cycle, then all the nodes in that cycle have to be in the same strongly connected components. So here's a very simple algorithm. I can say, find a cycle and say that everything in this cycle is definitely in the same SCC. So let's collapse this cycle and let's merge all of the vertices in this cycle into just one vertex. So for example, I take all the vertices here, I turn them into only one vertex. That would not change my strongly connected components, right? So I can keep doing this. I can find cycles and merge all of the vertices. So I find this cycle, I merge 7, 9, and 10. I find this cycle, and I merge 3, 4, 6, and 5. I merge 1 and 2 because even that is a cycle, right? And as I do this, at some point, I run out of cycles. And when I run out of cycles, each one of the remaining vertices is going to correspond to one of the strongly connected components of my original graph. Okay, that's the idea. We're going to do more of this in the next session. But of course, the thing that is interesting is how do you do this with just one DFS? So I want to do this in ON plus M. I want to do just one DFS, find all these cycles, merge all of them, find all the strongly connected components, do all of that. So I just say ON plus M by one DFS. And this is just my wish list. Okay. See you tomorrow.